Today we're doing another set of 2 with AMC 10B of problem 7 and problem 8 from 2022. Starting with problem 7, for how many values of the constant k will the polynomial x squared plus kx plus 36 have 2 distinct integer roots? Okay, so we have this polynomial here. Basically, it's asking us, so we have this constant k here, and for whatever value k can be, how much times can you factor it, I guess? Well, let's just start with 36. Basically, the number of ways we can factor 36 is the number of ways that we can do this except for the square. Well, 36, so the first one is 1 and 36, 1 times 36. Second one, 2, 18, because 2 times 18 is 36. Then it's 3 and 12. 3 times 12 is 36. 4 and 9. 4 times 9 is 36. And our final pair, 6 and 6. So we have all of these numbers here. That doesn't look so good, but still, just bear with me. So we want to find, so the key here is to use the constraints we were given. Now, normally, we would just get this number of 5 here, 5 of these pairings, and multiply by 2, since there's a probability when both of the numbers are negative. But in this case, we were given the constraint that both of these numbers had to be positive, distinct integers. Well, not positive, but distinct integers. When you use 6 and 6, this becomes a square, so this goes out. So now we just have 4 numbers here, and 4 times 2 is 8, which is our answer. And you multiply by 2 to include the negatives. Moving on to problem 8, consider the following 100 sets of 10 elements each. All of these. How many of these sets contain exactly 2 multiples of 7? 2 multiples. Well, here we notice after we multiply everything out, let's just test the first 10 terms of 7. The first 10 multiples of 7. 7 times 1, 7 times 2, 7 times 3. No, 7 times 10 is not. So 7 times 1 is 7. 7 times 2 is 14. 7 times 3 is 21. 7 times 4 is 28. 7 times 5 is 35. 7 times 6 is 42. This is 49, 56. And this is 63. So when we multiply all these 7s out, we see that, so we have 100 sets here. Each set has to have at least 1 multiple of 7, meaning that there is at least 100 7s in here. If not, if there's a weird case where any set don't have 2 multiples of 7, which is pretty weird, but that's probably not possible. But we just need to think about this. So each set has at least 1 multiple of 7, so it's going to be 7 times n. So 7 times some integer. And now the max value of 7 times n, whatever that is, so this is the last set till 1,000. 1,000 is not a multiple of 7, so this has to be less than 1,000 given the integer restraints. N is, n is less than 1,000, 7. So now we want integers, since all of the numbers are integers, so we have to take the floor of 1,000 sevenths, n is equal to 142. That's the max value of n now. Well, now here, 142, that's the max value of whatever n's there are. Now we have to subtract 100. And, why do we subtract 100? And what does this 100 represent? Well, 100 represents like the sets that have, so there's 100 sets here, and all the sets have at least one multiple of 7. So this represents the 100 set multiples of 7 here. You have 42 left over, which is our answer. But why 42? And why is that our answer? Well, recall that this 100 represents 7 100s. So when we subtract 100 from this 142, we get the remaining number of multiples, I guess, multiples that are not one, like, that don't have, the number of sets that don't have only one multiple of 7, I guess. So 42 is our answer.